Hello, this is Mr. Collier, and today we're doing some kinematics with vectors. Okay, so now we're going to do some word problems where the vectors are in context, like the motions of ships in 2D. So A again is going to be an initial position vector, and here T is actually going to stand for time, and B is still a direction vector, but now we call it a velocity vector, because it gives you direction, and the magnitude of B gives you the actual speed of the object. Okay, so B is going to be a very specific vector. It's not going to be any vector parallel to it. It has to be that vector, and the magnitude is going to be the speed of the object. So for example, this is the vector equation of the path of an object in time in seconds, distance in meters. Find the initial position, so that's when t equals 0. So if you substitute in t equals 0, you just get the initial position is 1, 9, if you want to write it as coordinates, or 1, 9 as a column vector, same thing. Plot the path of the object for t equals 0, 1, 2, 3. So the initial position is 1, 9. We can plot that here. That's at t equals 1. Then when t equals 2, we get, when t equals, so that's t equals 0. When t equals 1, we get 4 and 5. So we go over 4 and up 5. That's at t equals 1 after 1 second. And then we plug in t equals 2. Well, actually, we can see it's going to be all in a line, so we can go down 4, right 3, or right 3, down 4, as this vector indicates, right? So right 3, down 4, that's t equals 2, and then right 3, down 4, is that right? So over here at t equals 3. Find the velocity, the velocity vector. So the velocity vector is just this vector, and the speed is going to be the magnitude of 3, negative 4, which equals the square root of 3 squared plus negative 4 squared, which equals 5 kilometers per hour. Okay, this distance all the time is going to be 5 kilometers. E, if the object continues in the same direction, it increases to 30 meters per second, state its new speed. So this is actually 5 kilometers per hour right now. So if we want to get it up to 30 kilometers per hour, then we can multiply this velocity vector by 6, and we get 18, negative 24 is a new velocity vector. Okay, so let's take a look at this example. This question, I is east and j is north, just like normal ij vectors. Coast Guard station O, or the origin, constant speeds. Ship A starts at this point, travels with this velocity. Ship B is this point and this velocity. Show that they would collide if they maintain these velocities. So unlike normal vector lines, if you find a point of intersection, it doesn't mean that these ships are going to collide, because they have to intersect at the exact same time. Okay, so let's solve for the point of intersection. And let's write down the vector equations. So we have negative 5, 10 plus, let's say t, 2, 2 equals 3, 4 plus s, negative 2, 5. So we solve these simultaneous equations. Okay, we got 10 plus 2t equals 4 plus 5s. So these t's match up. So let's subtract, and we get negative 15 equals negative 1, and we got a negative 7s. And if you solve that, you get s equals 2. Okay. And now we go and substitute that into maybe this first equation to get the or I'll use the second equation to get the t value. Okay, so that's going to be 2t equals 4, t equals 2. So because those are the same, that means that at the point of intersection is after 2 hours, they will collide at the exact same point. Coast Guard told ship A to reduce its speed to IJ. Find the distance at 1400 hours. Okay, so we need to find both ships' positions after 2 hours. So the position of boat A is going to be -5, 10 plus 2. Now the new direction vector, or the velocity vector, is 1, 1. Okay, so that's going to be -3, 12. And for B, we have 3, 4 plus 2 times -2, 5 is -1, 14. Okay, then we can just use the distance formula. Square root of -3 minus -1 squared plus 12 minus 14 squared. That equals √8, which is 2 √2.